Good afternoon, everybody. My name is Boelo Schuur, and I'm the Scientific Vice President of the European Federation of Chemical Engineering. I've recently joined the board of the EFCE, and it is an honor for me to serve the community in this role. As a Vice President, it is my role to support our working parties and sections in their goals to promote chemical engineering in the widest sense to our society, to our fellow chemical engineers, but also the wider society in Europe and in the whole world. And hopefully that our wider society will benefit from our work as chemical engineers. Myself, I'm a chemical engineer, grew up in the north of the Netherlands and was trained at the University of Groningen. And since 2011, I work at the University of Twente. Although I have spent my whole career in academia, it has always been in very close contact with the chemical industry. And since 2023, I am also program director in separations for circularity at the Institute for Sustainable Process Technology in the Netherlands. So in this role, combined with my role in the EFCE, I hope to promote the collaboration between industries and academia, and especially the structures of our working parties where we have delegates from both industry and from academia. I think this should be a perfect match. I would also like to emphasize that, in my opinion, it is very important that we do things together. We seek for a sustainable future. We cannot do that as academia on our own, or maybe also not the industries on our own. And that is why I'm very thrilled to work at the EFCE in the structure where we can have this joint undertaking. Let me say a little bit about this webinar series. This is one in a series of 11 Spotlight Talk series, and in each of these talks we have 3 or 4, and maybe a rare occasion even more speakers. And in all these sessions we have specialists from the field that the working party or the section is presenting, talking about a topic of high importance. Since 2020, when the COVID year started, the pandemic started, we have hosted these spotlight sessions. And nowadays, this is something that occurs next to our in-person meetings. Because of the success throughout the years, we maintain this while we also get back to the in-person meetings. For example, next year, 8th till 10th of September in Lisbon, the European Conference on Chemical Engineering. And probably the working parties have each their own in-person meetings as well. But for now, it's a spotlight series online, and you can also register for the remaining sessions in the coming 2 days. You can find it in the same web pages where you found your registration for this webinar. Overall, I would like to mention that the EFCE represents chemical engineers in over 30 countries in Europe. And in total, we represent more than 100,000 chemical engineers. And our working parties and sections cover the most important topics in the field of chemical engineering. And we are at the core of chemical engineering field. I would like to close this introduction by thanking everybody in the working parties, specifically for today, the working party on drying and the speakers of this session. And of course also Martynenko for organizing these spotlight sessions. For now, I would like to hand the word to Maarten Schutyser for chairing this session on electrically driven drying. Maarten, the floor is yours.
Thank you very much. Let me share my screen. Okay, very nice that you came with so many. It's really a pleasure to host this webinar, this spotlight webinar. So welcome on behalf also of the European Working Party on drying. And we have composed together with my colleague Sulhaj Rizki, who's postdoc in my group. We composed a nice program, and I'm really happy that today we can have this talk. My name is Maarten Schutyser. I'm a professor at the Laboratory of Food Process Engineering of Wageningen University. Welcome once again. Maybe a little bit of background, let's say, why organizing this, this talk or this small symposium around this theme is that most of the current process technologies, they are still based on heating and using heat, in fact. So most dewatering and drying processes are thermally driven. So yeah, really we need a radical change, really a reduction in the use of energy, also because drying is one of the most, or is the most energy intensive unit operation, for example, food industry, and also many other industries. It is one of the more intense energy consuming process operations. And so we really need to use much less in dewatering and drying processes, but also switch to more renewable energy sources for processing. Of course, we cannot cover entire countries with solar panels to actually be able to supply the energy for all these dryers, because they consume a lot of energy. So therefore, it's also really important to reduce the amount of energy really needed to drive these processes. And of course, we could also say, okay, let's just stop with drying, but that's not possible. Drying is really important to preserve foods, to make functional products. And it's therefore also critical, not only, let's say, to remove water, but also to structure your product in a certain way to give it certain characteristics and so on. And so it's quite complex. It's not an easy task, because maybe then already people would have done it. But it's really important that also as researchers or industry, we're really seeking to novel solutions to not only use less energy with drying, but also look at, for example, electricity-driven processes that can also make use of electricity as a new renewable energy source. And so, for example, based on solar or wind energy. So moving from fossil fuel-based water evaporation to electricity-powered liquid removal, that's then the thought. So not per se, let's say, to heat the air of a spray dryer with electricity rather than a gas burner, for example. But one of the ideas is also to really use electricity as a means to really push out the water, let's say, from a product. And that's why we invited several speakers on different topics. So here you see an example of different dewatering and drying technologies. First, let's have a look at the dewatering technologies. So you could distinguish dewatering technology without phase transition, like mechanical dewatering, or reverse forward osmosis, but also the example of electro-osmosis, which will be touched upon by a speaker from the Technical University of Eindhoven. And of course, it's also possible to do dewatering with phase transition, like freeze concentration, evaporation, although these are, of course, more energy intensive. And so how nice could it be if you can use electricity as a way to pull out water from sludges? And in principle, the driving force, electricity as a driving force, is much more powerful than based on, for example, a temperature gradient or pressure gradient. So in that sense, there's a high potential. However, implementation of these technologies and scale these up is another challenge, but that will be touched upon by one of the speakers. Now then, of course, ultimately during drying, you want to also shape and microstructure product, which is actually the distinction between dewatering and drying. And while in dewatering, you just concentrate. In drying, you actually go to a final microstructured product. And of course, you can use electricity to heat up the air or use microwave drying techniques. But these are still, to a large extent, also thermally driven drying processes. Also freeze drying, contact drying, and many convective drying processes are thermally driven. But you can also use electricity to enhance their efficiency or to be able to also more mildly dry products. And those are, for example, electrostatic spray drying and electrohydrodynamic drying. And we'll hear more about these principles in our presentations today. So then we come to today's program. So we start with the introduction of Boelo Schuur and myself. Now then we'll start with two presentations. The first one on electro-osmotic dewatering and the second one on electrohydrodynamic drying of Sarthak, Mehta and Judith from Technical University of Eindhoven and Wageningen University. And both are PhD students, and they work in a bigger project called Electrified, in which we study 3 different technologies using electricity really as a driving force for dewatering. So that was one of the basic ideas to further extend that with extra speakers. And we're very happy that Professor Alex Martynenko will give a presentation on also electrohydrodynamic drying and the prospects of its for practical applications, all the way from Canada. But of course, online that's more easier than live. But I'm very happy that he's willing to present his experience on these technologies. And also a presentation from Chutani on electrostatic spray drying of whey protein isolate and lactose dispersions. And she is from the Irish Institute, the Teagasc Food Research Center. So happy that she is willing to give a presentation on this interesting novel spray drying technique, also enhanced by the use of electricity. Now, and then we have a short break in between of 10 minutes just to stretch our legs and have a bio break. And at the end of the session, we have a short discussion and conclusion. Now, if there are any questions, also after each presentation, we have a little bit of time to answer questions, but please put your answers in the Q&A, so using writing, and then I will ask the question or a select number of questions, depending on the number of questions, to the speaker. And maybe it's also good to know that all presentations will later be available through the YouTube channel of the EFCE. To conclude, I guess for now, if you have questions, you can leave them in Q&A. I would also like to point out that we have a LinkedIn channel of the Working Party of Drying. And also maybe interesting to know is that I'm organizing the next Euro drying in 2025 in Wageningen University, and it will be from 6th to the 9th of July. And here we have a logo and also a nice picture of Judith, who is one of the co-organizers and also the co-organizer of this spotlight session. So once again, thanks for your participation. And I think we can then start with the first presenter, which is Sarthak Mehta, for the first presentation. So then the floor is yours, Sarthak.
Thanks a lot, Martin. I'll just share my screen. Give me a second. I hope my screen is visible to everyone. Thanks a lot for being here. My name is Sarthak Mehta. I'm a PhD student at the Eindhoven University of Technology. And today I'll be talking about my project, which is electrically assisted membrane dewatering of biomass. So we know that the bio-based market is growing like never before. Earlier, food products were considered part of the bio-based economy, but now new products and new commodities are emerging in the form of packaging, biofuel, some of these examples. And the whole reason why we are moving towards a bio-based economy and bio-based products is because we want to get rid of fossil fuel. We want to move away from fossil fuel. And in order to produce these bio-based products, one of the key challenges that we come across is drying, concentration, and dewatering. The reason for that is that biomaterials are water-rich, and in order to store, utilize, and transport these said materials, it is important to go through this unit operation. Currently, this is done using thermal energy, as pointed out by Martin herself, and drying technologies account for 20% of the energy consumed in industrial processes. So it's very energy intensive. And because we use thermal energy mostly to evaporate this water, we lose a lot of energy in phase transition. Finally, because we use natural gas mostly to produce this thermal energy and dewater, it's kind of counterintuitive because we want to move away from fossil fuels, yet we want to use fossil fuels to dewater the biomass. Membrane dewatering offers a sustainable alternative to this problem. Most biomass dewatering using membranes is done by applying a certain pressure. So what we do is that we take a membrane and we pass a biomass slurry consisting of biomass and water through this membrane. In a common notion, the biomass is retained and the water permeates, separating the two phases from one another and giving us a dewatered biomass product. But the problem with this pressure-driven process is that the pressure is non-selective. It is equally applied on the biomass as it is on the aqueous media, pushing the biomass towards the membrane, leading to clogging and fouling. This leads to inefficient dewatering because now your permeate flux reduces and the operational pressure is significantly high. Therefore, we as KIC Electrified are a consortium that are working towards moving away from fossil fuel-based evaporation and moving towards an electrically driven dewatering system. Our consortium is divided into three work packages. Work package 1 deals with dilute slurries, work package 2 deals with semi-dilute slurries, and work package 3 deals with rather concentrated slurries. My work relies on work package 2, which is the adsorbed water in the semi-dilute slurries. The feed concentration for this work package is roughly around 20% volume by volume of solid content. So that's the feed we try to work with, and we try to dewater as much as possible. But before we move into my project specifically, I would like to step back and explain how electric field-driven selective migration actually works. Well, what we do is that we exploit the difference in polarities between the biomass and the aqueous media. Biomass in presence of water is always charged. And because of these charges, it is easy to manipulate and move them across the electric field lines when an electric field is superimposed. Now, when the biomass or these particles can move through the electric field, it is possible when the particles are too small. And this is referred to as electrophoresis. But what happens if the particles are too big? When the particles are too big, they agglomerate and they're not movable as they were earlier. They are immobile and they're stationary. But now what happens is the surrounding aqueous media starts to move in this electric field. How does that happen is better explained in the further slides. So, for surface charge formation, we want to understand how these surface charges are formed in the first place. How does biomass actually acquire this charge? And how can we exploit these charge formations for electro-osmotic dewatering? Now, imagine you have a biomass surface with hydroxyl surface groups. Imagine that these hydroxyl surface groups are exposed to a basic media. What we observe is that because of hydroxide ions present in the basic aqueous media, the hydroxyl group on the surface of biomass deprotonates, developing a net negative charge on the biomass surface. Because there's a net negative charge on the biomass surface, the surrounding aqueous media polarizes itself and creates an oppositely positive charge. When we zoom out, this is the figure we see, that there's a negatively charged biomass layer surrounded by an aqueous region of positive charge. Because of the negatively charged biomass surface, we first form an electric double layer. This is an instantaneous process in which there is a negatively charged surface surrounded by a thin layer of a positively charged aqueous media, and this comprises of the electric double layer. We can also measure the electric potential of the biomass at the edge of the electric double layer, and this is referred to as zeta potential. This potential is measured at the dotted line of the figure, as you can see. But because of the charged surface of the biomass, the potential is exerted beyond the electric double layer, and there is a localized diffusive region that is created just above the electric double layer. This diffusive region consists of positive charges to compensate for the negative charge of the biomass region. Another thing to note here is that the electric potential decays as we go along the y-axis. This decay is exponential, and we see that because of this exponential decay, the concentration of ions also decays as we go along the y-axis. This decay is characterized by the d by length. The d by length refers to what is the reduction of potential, what is the length at which the zeta potential reduces by 1 over exponential. So at a certain d by length, the potential will be 63% of the zeta potential of at the biomass surface. Now that we understand how these charges are formed in the diffusive region, what we do in a streaming potential experiment is that we apply pressure. In applying pressure, we are able to strip off ions from the top region. Let's assume we apply X bar of pressure in the diffusive region, and we are able to strip off the top layer of ions. As we increase the pressure, we are able to strip off ions from closer to the biomass surface. This is because as we increase the pressure, we are able to push ions that are more tightly bound to the biomass surface as they are closer and the potential is higher. When we increase the pressure even further, we see that we can strip off ions as close to the electric double layer. And this is referred to as streaming potential. We apply a certain pressure and we see a potential being generated as the ions are stripped off from the diffusive region of the biomass slurry. Experimental methods I want to cover before. Oh, my bad, sorry. Yeah, so I would like to talk about the experimental methods of the streaming potential setup. So what we do is we use non-porous silica particles of 0.1 mm diameter and we put them in a cylinder of 30 mm length. We close the cylinder with mesh electrodes. On one side we have the reference electrode, on the other side we have a sensing electrode. Now, as we pass an aqueous media through this packed bed of silica particles, what we see, a potential is generated across the bed. This potential is because of the ions that have been stripped off from the diffusive region, creating a net potential that is measured using the open circuit voltage and a voltmeter. I would like to bring your attention to the particle view and the pore view. Because we are dealing with a cylinder with particles dispersed around it, these particles show a rather unique behavior. In a particle, we would imagine that the surface is charged and the diffusive region is all around it. But in a collective nature of particles, it is the pore between these particles that has the highest diffusive charged region, and the electro-osmotic flow or the streaming potential is observed in this pore itself. So this is what the setup looks like. If you look at the image on the left, we see that the cylinder is filled with silica particles and we have these SS mesh electrodes that are smashed between, that contains these silica particles in between. So as we apply pressure, we are able to strip off more ions and we see an increase in potential. This can be also seen in the graph on your right. Some interesting notions that I want to point out from this graph is the values of pH 2 and pH 12. You can see that as you increase, as you go towards the extreme pHs, pH 2 and pH 12, the slope of the line closes down. This is because of shorter debye lengths. As the ionic strength of a solution increases, the debye length decreases. To explain that, if there are more ions present in a diffusive region, they will crowd the biomass surface, thereby exhibiting less potential to the diffusive region itself. And in doing so, the streaming potential value is rather low because there are not much ions available in the diffusive region. So we can see that in pH 2 and 12, we see lower slopes, but we also have another question to answer. Why do we see a reversal in polarity for pH 2 and pH 3? Well, that is better answered by the silica isoelectric point. What we observe is that unlike the basic media example that I gave earlier, in case of a strong acidic media, there's an excess of H plus ions. And these H plus ions or protons go and bind to the hydroxyl groups of the silica particle, thereby protonating it and giving it a net positive charge. Because the surface is net positive, the surrounding aqueous media is negative. And when you push it through the electrode, what we observe is a negative potential across the bed. Contrary, because we're dealing with basic media in the rest of the experiments, we see that the surface is negatively charged, the surrounding aqueous media is positively charged, and therefore we see that the potential is net positive. Well, when we use the given experimental data that we have received, and we plug it to the Helmholtz-Moltke equation, we can obtain zeta potential for the silica particles as a function of pH. Now, this zeta potential is extremely important because first, it gives us the information of what is the potential at the biomass electric double layer at any particular pH. And that is important because that is what will characterize the charge of the diffusive region and how it will move in an electric field. Contrary, because we're dealing with basic media in the rest of the experiments, we see that the surface is negatively charged, the surrounding aqueous media is positively charged, and therefore we see that the potential is net positive. Well, when we use the given experimental data that we have received, and we plug it to the Helmholtz-Moltke equation, we can obtain zeta potential for the silica particles as a function of pH. Now, this zeta potential is extremely important because first, it gives us the information of what is the potential at the biomass electric double layer at any particular pH. And that is important because that is what will characterize the charge of the diffusive region and how it will move in an electric field. We also understand a bit about the isoelectric point. The isoelectric point for this particular system lies between 4 and 5, somewhere around 4.2. This isoelectric point represents the point where the net charge of the silica particle is 0. Now, when we move forward, we understand zeta potential and we understand ionic strength and how it reduces the d by length. Before we move into electroosmosis, I would like to explain how the diffusive region is actually manipulated under an electric field. So when we apply an electric field, we start to strip off these ions from the diffusive region and move them along the electric field line or away from the electric field line based on the charges. So considering we have positive charge in the diffusive region for now, we'll assume that they move along the electric field line in positive x-axis direction. So as we start stripping off these ions in an electric field, we see that there is a shear plane that basically means the tightly bound ions, while move with the electric field line, cannot necessarily break the attractive force that is between the biomass surface and the ion present in the diffusive region. But as you go along the y-axis, the net potential experienced by the ions in the diffusive region reduces because of the exponential decay. And at some point, referred to as slip plane in the y-axis, we see the electric field force is sufficient enough to come over this attractive force between biomass and ions and lead to the slipping of these ions, leading to an electro-osmotic flow. So you can see the slip plane lies at some value of y, from where on the ions can freely move towards the other electrode and in line with the electric field lines. To give a better example of this, imagine that you are standing on a skateboard. The skateboard here represents the slip plane. As I pull the skateboard, the person sitting on top of the skateboard is also dragged with it. Similarly, as the slip plane is pulled, the person sitting or the water molecules that sit on top of this slip plane are also dragged with it. And in this process, we are able to not just move the water at the slip plane, but the bulk media using convection. Now, we understand that because of the pores, because of the silica particles coming together to form pores, it is actually the center diffusive region that contributes to the electroosmotic flow. We again use non-porous silica particles of 0.1 mm diameter, and we vary pH and ionic strength. Now, instead of measuring the voltage as we pass fluid through this particular bed, we rather apply voltage to this bed and see whether we can move water to the other side. We have made some modifications to the initial setup, as you can see here. If you notice on the right, you can see the setup that is modified with two cylinders measuring columns on each side to measure the amount of water volume that has been displaced when an electric field was applied. If you closely notice, you can see that there's a red dotted line referencing to the initial point, and after time t, we see that the water level has risen, suggesting that after applying a certain electric field, we can see that water is stripped out of this diffusive region and moves towards one of the columns based on the electric charge of the electrode. So we have a graph here that gives us time dependence of electroosmosis under different pH conditions. So we can see that for pH 12, we see that the flow is in the right-hand side or positive direction, whereas for pH 2, the flow is in the negative direction. That is because the silica particle polarity changes between these two pHs. And because of the change in silica particle polarity, we see that the flow is in different directions. The aqueous diffusive region is of different charges, and therefore, one moves towards the positive electrode, the other moves towards the negative electrode, and we can see a difference in the direction of flow. The second thing that I want to point out is the voltage. As we increase the voltage, we are able to push the water further. That is simply because with every increasing voltage, the force experienced by the ion is now higher, and it can overcome the attractive force to the biomass surface, thereby allowing for electroosmosis. One other thing that I would like to point out is that we see that the data stabilizes after a certain point, which tells us perhaps we should not talk about electroosmosis in terms of volumetric flow, but rather pressure. we see that as the water starts to move towards one of the columns and the column level rises, because of the new pressure head that has been created in the column, there is a back force that limits the amount of electroosmosis that is possible. So rather than talking about how much volumetric flow rate are we experiencing at a certain potential, we should talk about what is the pressure that has been created across the bed for a certain potential. We do this experiment for a wide range of pHs and we get this kind of trend line. An important thing to note here is that pH 2 and 3 experience an opposite direction of flow because they lie on the because they have a positive zeta potential, and pH 11 and 12 lie on the other side of the flow because they have a negative zeta potential. We don't see any electroosmotic dewatering for pHs 5 and 9 for two reasons. First, that the zeta potential, while does exist, it is the ionic strength also that contributes to this flow. If the ionic strength of pH 5 and pH 9 is of the order of 10 to the power minus 5 molars, there are not enough ions present in the diffusive region to push the water to the other side of the column. The second thing that I would like to point out is while the zeta potential of pH 12 is higher than the zeta potential of pH 2, we see that the electroosmotic dewatering is better for pH 2. That is also because, and in case of pH 2, the surface is positively charged, which means the surrounding diffusive region has more of hydroxide ions present rather than initially protons being present. And because of these hydroxide ions having hydration numbers higher than protons, we see that pH 2 shows higher dewatering because as a hydroxide ion is pushed to the other side, so is the hydration shell that it consists of, and we see more water is pushed to one of the columns. Another way of looking at this particular thing is that you need to take into account that as the debye length reduces, your diffusion region becomes more dense and more prominent. And therefore, this slipping plane and the convective term is way more stronger. To give an example for this, imagine that you have an air mattress and imagine that you have a hardboard. Now, the hardboard represents a smaller debye length and a tighter, denser debye length, whereas an air mattress represents a rather diffused region of with a larger debye length. So if you put something on a hardboard, you can pull it faster. But if you put something on a air mattress and you pull it, the chances are that the object cannot move with the air mattress. So as your debye layer becomes smaller or denser, it is easier to strip off ions from that region. This is also explained with this. So if it is easier to dewater systems with higher ionic strength, does salty water dewater faster? Yes. While I cannot show the results in this presentation, but we have concluded so far that as we increase the salt concentration, we reduce the debye layer and therefore can strip ions faster. One thing to note here, and which is a very peculiar thing, is that as I increase the salt concentration, I see a reverse in polarity. As you can see for a 5 millimolar KCl solution in pH 3. This reversal in polarity can be discussed with the shielding effect of the ions. Because of a negatively charged surface, the ions are shielded, and because the ions shield the negative charge, and at a certain concentration of ions, those diffusive region does not experience any potential from the biomass, but the potential of the shield itself. So instead of experiencing negative charges that it would have earlier, now it experiences a net positive charge. And in doing so, the streaming potential changes. So the reversal of polarity is because of a shielding effect, and the diffusive region now experiences the ions instead of the biomass surface. To summarize, the electric field that is responsible for electroosmosis is uh, essential, but so are zeta potential and ionic strength. While zeta potential is important to create the diffusive region, it is actually the ionic strength that leads to electroosmosis or water migration under the electric field. And as I said earlier, as we increase the salt concentration, we reduce the debye length, increase the ionic strength, and see better electroosmotic dewatering, which I cannot, of course, show in these experiments so far. Thanks a lot for your kind attention. I would like to thank KIC Electrified Consortium, which consists of 8 industrial partners and 5 academic partners. Please feel free to scan any of the QR codes if you're interested in the research that we do at my research group, Membranes, Materials, and Research Processes at the Eindhoven University of Technology. Thank you.
Thank you very much, Sarthak, for your very nice presentation, also sticking to the time.
Yes.
So very well done. Yeah, so the floor is open for questions. Below your screen, you can find the Q&A button, and there you can write down potential questions you might have if you're curious about this technique. So far, I don't see any questions. I don't see any open questions. So maybe just from my side, a question. On the electro-osmotic setup or flow setup, you chose to build up a pressure. Could you simply translate that to a setup where you actually go towards dewatering, or then you might run into different type of issues, or why did you choose for this particular setup?
So the reason why we started with this setup in particular is because when I was working towards dewatering, we wanted to make sure that the bed is always saturated. So when I start dewatering, there will be a time when there is lesser water in the pore, and that will make the pore collapse. And that will eventually lead to higher electroosmotic dewatering because the diffusive region inside the pore is now experiencing higher potential from the biomass surface. We didn't want that to happen because that's an additional complication that we don't want in our experiments early on. So we created these columns to basically act as reservoirs, so that when the water is moved through the bed and the bed does not dry, the water from one reservoir can simply enter the bed as the other one rises. It is when we were doing these experiments that we realized that perhaps the electroosmotic flow is not constant, because as you can see from the graph, it stabilizes over time. We see that a certain height is achieved in the column, and that is the height at time t equals 100 minutes, at time t equals 600 minutes. So that column height does not change after a time, suggesting that we should not perhaps consider, and most research papers talk about milliliters per minute or microliters per minute of water produced in electroosmosis, but it is at the end of the day the electric field force that is moving the water. And since we are talking about forces, pressure is a way better term to explain the phenomena we observe rather than volumetric flow. I hope that makes sense.
Yeah, and that's by that knowledge you can actually in the end also come to a design that focuses more than on real dewatering, I guess.
Yes.
Yeah. Okay, thank you. I see that there is here a question from Eindhoven via the Q&A. So have you any thoughts about particular applications where this technology might potentially be exploited to reduce or replace thermal energy use?
So if you want end game application for this, I genuinely see that this could, if you remember, if you know how paper industry works, we use this conveyor belt system that consists of several rollers, and you heat up these rollers to then dewater or dry your paper as it passes through the conveyor belt. Now imagine, instead of using heat as a way to evaporate, these conveyor belts are made of electrodes, charged electrodes. So as you pass the slurry or sludge through this conveyor belt in between these two electrodes, and you apply an electric field, you can drip off water, specifically targeting water and not the biomass. So your energy is conserved because you're only using the energy to move water, and at the same time your dewatering is sustainable. So that's how I see it being used as an end case application for conveyor belt drying.
Yeah, very nice answer. And maybe a bit of follow-up question from my side is then also the kinetics is important. So how fast the process happens, because drying of paper is usually done at a very high speed.
Yes.
So that's really something to look into. Is that also something that you will look into?
The interesting thing about this is that we are not limited by the area. So as long as the electrode area to the area of your sludge is concerned is maintained, you can go to 1 meter square, 100 meters square, your dewatering rate will stay the same. So in order to increase the capacity of dewatering, I would say we expand on the area while keeping the potential and the rest of the conditions same. So we can dewater at a faster rate, meeting the industrial requirements. While the process might be slow, the area by increasing the area, we can meet the industrial demand still.
Yeah. Now you here also on this slide see clearly that by increasing the voltage, you also increase
By
the
increasing
speed
the voltage, we can also,
of dewatering in principle. Yeah. Okay, I don't see any further questions. So we had a nice discussion. So I think thank you once again, Sarthak, and I would say give an applause, but that's a bit difficult online.
No worries, no worries.
Thank you very much once again.
Thanks a lot, Marteen.
So then I would like to invite the next presentation. Yeah, I see here. Now the next presentation of by Judith Ham from Wageningen University. Maybe you can open your video and share your screen, Judith.
Yes, I think my screen should be visible, right?
Yes, it is. So
Great,
the floor is
then
yours.
Thank you very much, Maarten, for the introduction. So yeah, I want to start this talk today by asking you a question, namely the difference or which of these different fruits tastes better. I'm sure all of you have a preference for either apples or pear, or maybe you think they're both disgusting, but it's an answer you can answer quite quickly, right? A different question would be which one of these fruits dries better. And I think that's a bit harder to answer. Maybe one of them dries faster, but maybe the other one will have a better quality after drying. So what is then better? I'm researching in equipment design of a new drying technique, namely electrohydrodynamic drying. And for this, like any starting researcher, I looked into literature. So I found in this first paper that EHD drying is more than 8 times as efficient as hot air drying. And this is huge, right? But then a second paper said that EHD drying is only 25% more energy efficient. So that's already not that much anymore. Now, you can say, okay, maybe the setup in the first paper is then way better. But maybe the setup in the second paper, where it actually only takes 4 hours of drying, is better than the first paper, because fast drying is for industry quite relevant. Now, my question would be, what is the difference between these setups? I already see in the title of these papers that one dries tomatoes and one dries mushrooms, but I can also tell you that one only uses EHD drying, while the other combines EHD with hot air drying. So maybe the first one is better, because it's very energy efficient. But maybe the second one is better, because it dries very fast. Now, for me, I want to tell you today about design choices we can make in dryer design to choose the best drying setups. So today I want to tell you about electrohydrodynamic drying, and then especially the experimental characterization of an ESD drying setup. My name is Judith Ham and I'm from Wageningen University, and I hope to give you a bit more information today about design choices. So electrohydrodynamic drying is a new drying technique where we use a small electrode surface. This is either a pin or a wire, and on this small electrode surface, we apply a very high voltage of the range of kilovolts. If we apply this high voltage, the air around the small electrode surface will ionize because of electrical discharge. If we then supply a collector electrode that's either grounded or is of opposite charge, the ionized air will start to flow. This will create an ionic wind because the ionized air molecules will drag along non-ionized air molecules. If we then supply a material, we will enhance convective transfer of moisture from the material to the bulk air, and this way enhance drying. Additionally, the ions that will stack on top of the material surface will cause an electrical field being drawn over the product, and this can enhance internal moisture transfer. Now I will study ESD drying in an experimental setup, which you see here on the left, but as it's a bit hard to explain by a picture, I also draw for you a more simplified setup. So the main thing that you see for a setup is a wind tunnel, which is shown with the dotted line, or here in plexiglass around. Through this tunnel, wind can flow, and wind will start to flow because of our ESD mechanism. We have an electrode which is coupled to a high voltage supply, and this electrode is a thin wire electrode. In the picture, you can see that based on the red wire. We also have a collector electrode that is grounded and that is hanging from a balance. In that way, we can monitor water removal based on weight during drying. Between that collector electrode and the ground, we have this system of one resistor and a voltage meter, and that way we can determine the current that is flowing through our system. And as we know the current and we know the voltage we supply, we also continuously know the energy consumption of our system. Now we cannot do everything in an experimental setup, so we also have some need for modeling of this mechanism. For that, I have my colleague Zulars, and he works with a setup that is very similar as mine. Instead of this dotted line or the plexiglass system, he has this large square. The emitter is this small round, and this line is where a collector electrode of any width can be placed. And the smaller square is then the location where the mesh is a bit more refined. Experiments that I can do with my own setup are that we can vary the electrical potential that we apply, but we can also vary the setup parameters. We can vary the emitter electrode. We can change the material it is, but we can also place it farther away or closer by the collector electrode. We can also place it to the side, so we can change the position relative to the collector electrode, or we can use multiple electrodes. Further, we can vary the type of collector electrode that we can use. For example, we can use meshes, but we can also use plates of different sizes. And lastly, we can also, of course, change the product that we are drying. But as I'm focusing at the moment on design parameters, that one I leave out for now. So let's first focus on this collector electrodes principle. Now, based on modeling, we already see quite a difference in the system if we use either a mesh or a plate electrode. As I explained before, the ESD mechanism is based on creation of a wind. And if we use a mesh electrode, this wind can form a wind jet. So the ESD jet can pass through the mesh, and this way it generates quite high wind velocities, but they keep located at the center. Meanwhile, if we use a plate, not as high wind velocities are used, and the wind jet is actually distributed more over the area of the full plate. So it's more divided. I'm sorry. You also see that after the wind is bended upwards over the plate, it will move upwards. Even though the plate here is only part of the channel width, very little wind will bend upwards to the bottom side. Most of the wind will move upwards due to pressure differences. This is also something you can see based on our materials that we are drying. So in this figure, you see a maltodextrin film that we dried. And one thing that catches my eye immediately is the lines that you see. So in the center, you see lines that are in parallel to the wire electrode that we placed. And on the sides, you see lines that are perpendicular to the wire electrode. And they're actually quite similar to what we expect based on modeling. So these lines in the middle are caused by the impact of the impinging jet, while the lines on sides are actually due to the wind bending upwards from the middle and creating kind of an airflow path. Something else that you can notice is this very bulky gel-like structure on top. This is due to an experiment where we didn't place the plate completely leveled, but we had it a bit tilted. The idea was that in that way, we kind of can guide the wind downwards to the path of the least resistance. So you can see that here, that if you have an impinging jet that goes down, we expect the wind to bend upwards to the downside because it experiences least resistance. But what you also can expect is that due to gravity, most of the sample will also be at the bottom side of the plate. Now what you then see is the upper side of the plate, even though it had less sample, it also dried less because it experienced less wind. Meanwhile, the part with most sample, the bottom side, was drier because it experienced more wind. So based on this, we can say that a good dryer should generate a wind flow, sufficient wind flow, and that drying is therefore dependent on the wind flow. For this, we looked a bit into the literature and we found that wind flow is actually dependent on current. And current, as you can see in this figure, will increase if you apply a higher electrical potential. In the same way, if you have less space between the electrodes, the current will also be higher. So if we have 4 centimeters between the electrodes, we achieve lower currents than if we have 1 centimeter between electrodes. For this, we have an equation which states that current is dependent on a geometrical constant, the electric permittivity between the electrodes, ion mobility of the air, and an onset voltage. And the onset voltage is the minimal amount of electrical potential that is needed for current to start flowing. Below this onset voltage, the amount of energy you're supplying is not sufficient to bridge over this air gap in between the electrodes. If the distance between the electrodes is higher, the onset voltage will also higher. Meanwhile, the geometrical constant will get lower. We prefer to have an onset voltage that's as little as possible because that's a way we can generate high currents and therefore high wind velocity. Onset voltage is linearly dependent on distance between electrodes, but you can also see that even though it goes down and down and down, we don't reach an onset voltage of 0. This is partially because of air resistance. Like I said, we really need a minimal amount of energy to jump over that air gap, but there are also other influences. We see, for example, that the electrode material that we use affects the onset voltage, and we see that the product material that's placed between the electrodes also has an effect. A very wet product is more conductive, meanwhile a drier product is less conductive and therefore contributes more to that minimal amount of energy that is needed to jump that air gap. Now, as I said, all of this is in order to generate the highest amount of wind velocity that we can generate. So what we did is to try to see if we can measure the wind velocity. On the right, you can see part of our setup. So on the top, you see the mesh electrode that we can use. and below that you see our anemometer. Our anemometer needs to fit in the tunnel, so we place it in parallel to our wind jet, and it's quite far below the mesh in order to not disturb the electrical fields between the emitter and the mesh. What you see is that wind velocity we found to be related to the square root of the current and a whole lot of constants. And if we then insert the equation for current that I showed you before, we have the square root of a whole lot of constants, so the distance between electrodes, geometrical constant, the electric permittivity, the area of the collector electrodes, and the density of air, and again that voltage and onset voltage. And for high distances between electrodes, as you see here in the crosses, that's a slope. So these constants that we bunch together is actually lower than if the distance between electrodes is low. So the triangles. So even if this DEC gets lower, the full slope will become higher. And that's all because of this geometrical constants. So what we would like is to explain what influences this geometrical constant in terms of the types of collectors you use, the types of emitters you use, the distances between electrodes, but we also see material effects of the different electrodes that affect the geometrical constant. Now, as I said already, we placed our anemometer in parallel to our wind jet. Meanwhile, the anemometer measures wind coming through its tip. So we don't measure very accurately. So we want to compare the data that we measure here to what we would calculate on as the average wind velocity on the mesh. And that you can see here. So on the x-axis, you see that average wind velocity over the full width of the ground electrodes. And here you see on the y-axis the measured wind velocity. And what you see is that we actually measure quite in the same order of magnitude. And we see the same slope. So we measure quite accurately, but the wind velocity that we measure is a bit underestimated compared to what would we actually expect. And this has three reasons. First of all, like I said, we measure with the anemometer in parallel to the jet. Meanwhile, we would measure more if we place it perpendicular. Secondly, we don't measure exactly on the mesh. We measure 10 centimeters below, and we have to do that to not disturb the electrical field. And thirdly, we measure only on a very small distance, just below, directly below the mesh, and directly below the emitter. Meanwhile, the air jet might be wider than the region that we measure. So that we tested with modeling. In this graph, you see the velocity magnitude of the air on the collector electrode, where the radial position of 0 is directly below the emitter, and a radial position of -7 is completely to the side, and radial position of 7 is completely to the side of the wind channel. For a distance between electrodes of 1, you see that actually the full air jet is located in the center of the wind tunnel. And on the sides of the wind tunnel, actually no wind velocity can be measured anymore. Meanwhile, if we increase the distance between electrodes to, for example, 3 centimeters, the wind velocity that is measurable on the sides is actually quite noticeable. So the wind jet is way more distributed and is not really a jet anymore. So the measure data that we tested is actually not taking into account this wind flow on the side. And therefore, we mostly use the equation that I just showed you for the average wind velocity on the mesh. So until now, I talked to you a lot about the design parameters to generate a high wind velocity. But we also want to look a bit more further in how to generate an efficient wind velocity. So in this graph, you see on the left the average wind velocity based on the equation I showed you before. And on the right, you see the efficiency to generate this wind. So the amount of kinetic energy per electrical energy unit that we supply. And a very positive thing came out of this, because what we concluded was that actually quite high energy efficiencies in the blue icons, or the highest energy efficiencies, were found at the highest wind velocities. And that the highest energy efficiencies were also found at the highest electrical fields. So in order to generate fast, we need high electrical field strength, so either at high electrical potentials or at high distance between electrodes. But we don't only drive fast then, but we also drive very energy efficient then, which is beneficial which allows us to make both the best drying setup, either with the fastest drying, but also the most energy efficient drying. So I hope next time someone asks you what is better drying, I hope you think to yourself, okay, we have different ways to conclude how something dries fast, but in ESD drying it actually doesn't matter, as fast drying is also energy efficient drying. And I hope that this convinced you of that. Thank you very much.
Thank you very much, Judith, for your nice presentation. Very informative, I guess, for many people who are not so familiar with EHD drying. I guess Alex Martynenko knows a lot about EHD drying. So if you have any questions, Alex, please go ahead. If other people have as well. Maybe just to kick off, I have a small question. And so in the last slide, you showed something about efficiency, and there you concluded that increasing field strength and reducing distance would be the way to go to be more efficient. But of course, there's a limit to distance, and there's a limit to field strength. Or are you at optimum already, or can you speculate a little bit on that?
Well, I think the limitation would mostly be because of safety. So if you operate at very high field strengths or at very low distance between electrodes, then you will generate glow discharge, or you will cause sparking of the electrode. So this will then start to this way you will enter a new energy regime, and this will not be very energy efficient. As you generate a glow, you generate light, and then not all your energy will go to motion anymore.
So then you become less efficient again.
Yeah. So there will be an optimum there.
Yeah, it's not very much desire to go to this risky region, but yeah, you're almost there, let's say. So that's, yeah, it's still safe, but you don't want to go any closer than 1 centimeter, perhaps. Yeah.
Exactly. Yeah.
Okay, I see a comment that great presentation, congratulations, and I also see that a question has the polarity of the electrical potential applied to the wire. Is it important for the process? Maybe. Yeah, so I guess negative to positive or vice versa. Is that important, or ground versus positive, or the other way around, let's say?
Yeah. So in air, we of course have different molecules. So we have oxygen, we have nitrogen, and as in my system, we use a positive polarity. which will cause a positive ionization of the air, which is quite efficient. We could use a negative polarity, but then we would ionize other type of molecules. And that would be for just air, less energy efficient, but then you could try to choose other media. But to keep it simple and to keep it maybe a bit safer for industrial applications, we chose to look mostly at air.
I guess maybe you also see the questions, also a little bit about how many kilovolts, until about 20 kilovolt I saw that you apply concerning field strength.
I'm sorry, how many
kilovolt do you apply?
Yeah, I work between the 10 and the 20 kilovolts mostly.
Does the drying take place in the nitrogen atmosphere, taking into account process safety?
In nitrogen atmosphere, we generally just work in air.
Air, and that's safe, huh?
Yeah, just ambient conditions.
Yeah, ozone generation might be a risk. I'm not sure if the person is referring to that, for example, but you had a check on that, huh?
Yeah, so we did build a cabinet surrounding the setup, as we expected to be some ozone generated there by the electrical discharge. But we found that this was very minimal, not more than on a sunny day in a big city.
Yeah. Great. So how is the wind generated? Is the wind generated by an electric field more efficient for drying than wind by mechanical means? A fan, for instance. Is there an additional thermal effect, and does it contribute to the energy efficiency?
Well, I would say for mechanical wind generation, the biggest drawback would be the air resistance of, for example, the fan itself. While for ESD drying, we really directly translate the electricity to momentum, and we don't have many resistances like the air resistance. Yeah,
so you say that it's a bit more efficient than conventional use of a fan.
Yeah, so the efficiencies that I also showed in the last slide were up to about 5%. Fans would be about 1%.
Yeah. All right. Yeah, there's no thermal effect or so, I think. I think these were. We still have a few minutes. So maybe I had another question, because now you showed a batch drying device, in fact. So how would you scale this up, this technology? Is that possible, or how do you envision that?
Yeah, so the figure that I showed you of the maltodextrin drying, you already saw that the sample is impacted by the jet and the shape of the wind. So I think it's very important to consider a moving sample. And then, for example, generate multiple wires next to each other. So the sample experiences both high wind velocities, so the jet, but also the non-high wind velocities, so the sideway bending wind flows. But that we expose it to not only the jet.
Yeah, so then it's also more homogeneously dried, the product.
Yeah.
Here another incoming question. So does the flow of charged particles add to the drying effect? So that's a nice question.
Sorry,
the flow of charged particles, because there are ions, let's say, bumping into the product, does it add to the drying?
So we expect that so we know that charges will stack on surface of dielectric materials, of which food films would be one. And these charges, layering on top of the sample will cause an electrical field over the product. And because of this, there would be some mechanisms that we expect, like electro-osmosis that my colleague Sarthak just presented, to be taking place because of that.
Yeah, and it might possibly enhance internal diffusion of for example, water, but also other components. Maybe a last question here because of time. Does high circulation of air for a non-mesh case can increase the chances of saturating air? If so, will that affect the drying? So I guess that the relative humidity will increase.
Yes, that's definitely something we want to consider for drying setup. Indeed, because the moist air after drying will bend upwards, there's this air recycling, while for a mesh system, it will be directly disposed at the bottom of our system. So we are trying to think of ways such as supplying fresh air to minimize this effect. But if these air would get saturated, indeed, it would affect drying.
Yeah, you don't want the relative humidity to raise too far and reduce the drying rate indeed. Yeah. Okay, thank you very much once again, and also thanks everyone for the nice questions, which really nice and further elaborates on the presentation. So thank you once again. Also thank you once again, Judith, for your nice presentation. Then we now have a small break for about 10 minutes. So in 10 minutes, 15:50, we will continue with the presentation from Alex Martynenko. Hope to see you back, and please stretch your legs and grab a cup of coffee or tea. Yes.
I would also like to mention a couple of other challenges. I have a couple of minutes, and this is related to erosion of electrodes. And for ideal work, we need to use either molybdenum or tungsten electrodes, not stainless steel electrodes, because they're pretty much wearable material. However, it will imply additional cost on the industrial scale dryer. So this aspect has never been explored, but mechanical degradation of emitters might be a big issue for industrial scale equipment. Also, another issue is efficient dehumidification of the air. The problem is that if we create mechanical airflow, it probably will damage EHD effect. This was explored in a couple of papers. So we are limited in terms of ability to remove airflow from the drying zone. And that's what requires additional technical solutions, how to dehumidify air. And one of them is using absorbing type of dehumidifiers. So what issues should be solved in the future research? First of all, we don't have mathematical model of all of EHD effect. Means that in EHD effect, we have coupling of mass, energy, momentum, and charge transfers. For this particular case, nobody really developed the reasonably good model. And that's what we are doing right now. We are working on combining of all of these effects into one coupled type of model. Also, the role of spatial charge in electrostatic induction and mass transfer is not clear. Effect of material properties and thickness, microstructure, electric conductivity on mass transfer is not clear. So unfortunately, we are limited right now only with like thin layer drying, because what we know that EHD have only convective mechanism of drying, and nobody really explored electrodiffusion part of EHD effect. And definitely effect of EHD on the quality of high value biomaterials, it's under exploration. And I see that recent papers, which are mostly published by Chinese researchers, are mostly concentrated on probiotics, nutraceuticals, enzymes, and functional foods. So it's a great opportunity for future sustainable drying. I just gave example of Canada, where we used almost 330 of pentajoules per year of energy for drying. And here is just sectoral use. It cost industry $9.1 billion. Replacement, just simple replacement of convective dryers with AHD would drop energy consumption significantly, like 6 times. Definitely carbon footprint would be reduced. Social benefits, premium quality product, cleaner environment, climate changes, and the most important, that AHD is low-cost technology with significant innovative potential. Thank you for your attention, and I would be happy to answer your questions.
Thank you very much for your interesting presentation, Alex. And I think really nicely complementary to the presentation of Judith, who was a little bit more into details of a specific setup, and you broadened it to give a bit of overview on scale up and application. So really nice also to see that you started really building and implementing your knowledge into commercial equipment in the end to actually make the impact. But I could guess that there are some questions. Yeah, I see here a first question from Ein Kemp. If energy use is less than the latent heat, logically either some water is being removed in liquid form or the heat of evaporation is being supplied by another source. For example, evaporative cooling of the airflow.
Thank you,
Which
Jan.
is it?
That's a good question. So some water probably is removed in liquid form, so it's just electric field pulling water in water molecules in liquid form. But also we could consider that part of the heat is coming from the outside surrounding air, which facilitate evaporating of the air from the surface, of the water from the surface. So both.
So the energy consumption that you take into account is only the electricity to generate
the energy
electricity.
consumption is related to electricity and the auxiliary
Current.
equipment.
Yeah, and not per se to.
And what is interesting, I would like to add to this. So in the extreme case, if we will ignore, let's say, drying rate, we could limit ourselves with 120 kilojoules per kilogram of evaporated water. But it will be very small drying rate.
Yeah, and here a question from Johan Padding. Thank you for a great talk. What is your view on the role of ions that impact on the surface of a material to be dried? Can you explain how, in your view, the electric circuit from emitter to ground electrode is closed?
Sorry.
Yeah, so in principle, the ions that are, let's say, inducing the ionic wind, they bump into the surface. So how do they move towards the grounded electrode, which is below the product, I guess, and thereby close the circuit?
Actually, the product which is lying on the ground electrode is conductor itself. So the ions are mostly concentrated on the wet parts of the material, and that's what creates selective action of electric field. Ions on the wet material. So, for example, if you will put exposed to this AHD unevenly wet material, so the most effect will be on the wet parts of the material, just because of more electroconductivity.
Yeah, and then gradually this effect declines when the product becomes drier. Yeah,
it will create more uniformity on the surface.
Yeah,
and uniformity in terms of electrodiffusion.
Okay, great. Yes, maybe a small question from my side. So how do you think, so that let's say, because in principle, EHD externally or enhance external heat and mass transfer, but also there would be some internal effect. Did you look into these, the contribution of these different phenomena? Could you say something about it?
You mean internal effects? Electrodiffusion?
Like enhancing diffusion,
Yeah, definitely. We still don't know what the what the reason for enhanced diffusion coefficient, either increased gradient of moisture content or direct effect of ions. So we need to make a focused set of experiments to answer this question. But this is very good question. This is the question probably which will allow you to answer what is the role of electrodiffusion in all this game, and maybe it will open opportunities for drying of more thick materials, not only thin.
Yeah.
I
Okay,
see a
thank
lot
you.
of questions from the
Yeah.
audience here.
Yeah, no, but most were already posed, or were still, let's say, of the previous presentation. I don't see any new questions. Also, in view of time, I think we have to proceed with the next presentation. So, but really interesting. I think we can keep on talking on this topic. So, but once again, thank you, Alex.
Thank you very much,
yeah,
Maarten. Yeah.
And then we continue with the last but not least presentation from Chutani. She will tell us something more about electrostatic spray drying. So I'm very curious also to this presentation. Maybe you can share your screen.
Thank you, Martin. Yeah, can you see now?
Yes, not in the presenter mode yet. But
can you see my screen?
Yes.
Okay.
Yeah, now also in the presenter
Hi, everyone. Thanks, Martin, for inviting. Sorry. Yeah. Thanks, Martin, for inviting me to this event. So there were really interesting talks from Alex, Sarthak, and Judith about electrically driven dewatering technologies. But I could see those technologies work on solid or semi-solid products. So let's see how an electrically driven dewatering technology works on liquid products. Hello again. My name is Chutani. I'm a PhD student based at Teagasc Food Research Center, Ireland, and I'm also affiliated with Wageningen University and Research Netherlands. Dr. On Murphy from Teagasc and Professor Tom Huppertz from Wageningen University and Friesland Campina are my supervisors. So today I'm going to present on a new technology, electrostatic spray drying, and its working principle and its role in the drying of whey protein isolate and lactose dispersion. So first, let's start with a brief overview of spray drying. We all know spray drying is a widely used method in the food industry for converting liquid products into dry powders. So this process broadly it involves the feed is pumped through a nozzle which atomizes the liquid into the small droplets. These small droplets are then exposed to a very hot air of temperatures around 150 to 50 degrees Celsius to a drying chamber where there is a rapid evaporation of water taking place and resulting into formation of dry particles. So electrostatic spray drying is a slight modification of the conventional spray drying process. Here, an electrostatic field is applied to the liquid feed. So this electrostatic field imparts an electric charge to the droplets that are forming during atomization, which makes it possible to dry these droplets, the atomized droplets, at low temperatures, like starting from 75 degrees to it can go up to 150 degrees, and then resulting into dry powders. Now, you may wonder how an electric charge enables such low temperature drying possible. So let's find out. So the droplets, so the components in the droplets are charged. They go under stratification. So by stratification, I mean when you charge a droplet, it drives out the most polar part of the feed. So which is typically water, the food products. And to the outer surface, and the non-polar part of the feed tending to remain at the center. So this stratification in the components boosts the drying rate and allows drying at lower temperatures. So even we can go at outlet temperatures as low as 30 degrees. And another advantage of this technique, electrostatic spray drying, is that it is an inert atmosphere drying. It operates at less than 1% oxygen, so which can provide oxidative stability to the powders as well. So if we talk about the drying temperatures in both the techniques, conventional and electrostatic spray drying, so you can see the inlet temperature ranges in this spray drying is 150 to 250 degrees Celsius, giving outlet temperatures of 70 to 90 degrees. Whereas in electrostatic spray drying, the lowest inlet temperature could go up to 75 degrees, and the outlet temperatures could be as low as 30 degrees. So, so this technique holds a great potential in drying heat sensitive components or volatile components per se. So today I'm going to present a study which is the drying of whey protein isolates and lactose dispersions, and we'll see the comparative effects of electrostatic spray drying and the conventional spray drying method. So here we chose a dispersion of whey proteins and lactose. So since whey proteins are heat sensitive proteins, so we'll find out how electrostatic spray drying achieves the target of let's say preserving its native state. So first a dispersion was made of both the ingredients in the ratios similar to what is normally found in an infant formula. So next, so the methodology was first, like I said, a dispersion was made in the ratios 1.3 to 7.2, and then its pH was adjusted to two levels, 3.5 and 7. So these two pH levels were selected on the basis that the whey proteins would have equal and opposite charges on them at these two pH levels. And after that, its conductivity was adjusted at 25 degrees Celsius to two levels again, 3 and 4 millisiemens per centimeter using salt. Finally, drying was performed in an electrostatic spray dryer at 90 degrees Celsius and 10 kilovolt charge, and in a Bookie mini spray dryer at 170 degrees Celsius. So both these models were at laboratory scale. So, so these are the processing parameters for both the drying methods. So our idea was to keep both the processes, both the drying processes as similar as possible, only varying the temperatures. So we kept the feed, for this we kept the feed to drying gas flow ratio constant. And here we achieved an outlet temperature of 35 degrees Celsius in ESD drying, and for CSD drying we achieved around 85 degrees Celsius outlet temperature. So both the drying methods generated moisture contents of satisfactory levels, that is below than 5%, and water activity levels below uh, zero point 0.2 to zero point 0.3. So for the analysis purpose, we looked into the zeta potential values before and after drying on the whey proteins. So here yellow represents the zeta potential value before drying for the regional dispersion. So the blue one shows for the ESD powders, and the green one shows for the CSD powders. So you can clearly see that CSD powders tend to be less charged. The proteins in the CSD powders tends to be less charged than ESD powders, where ESD powders are retaining, like the proteins in the ESD drying are retaining most of their charge. Now the question is it because we are applying an external charge in the electrostatic spray drying, or is it because the proteins are getting denatured during the high temperatures that are encountered during conventional spray drying method? So let's find out. So like to confirm this, we looked into the denaturation profiles of whey proteins in a DSC. So here, like you can see from these two graphs, so this is for EST powders, and this is a profile for EST powder, and this is the original dispersion before drying. So you can see clearly see the troughs in the graphs, both of these graphs, which indicates denaturation. But the CSD powders didn't show such behaviors. There were absence of such troughs. So we can say that we can say that the proteins were already denatured during the drying process, and they didn't and the troughs didn't come up. We can say that the EST powders indicates the presence of native proteins after drying, which may also help them retaining their zeta potential. And further, we looked into the conformational behavior of whey proteins using FTIR spectroscopy within the amide 1 region. Here you can look at the secondary derivative spectra of ESD and CSD powders at both pH levels and the native whey proteins before drying. So here you can see that ESD powders match the conformations as originally present in whey proteins before drying. But the CSD powders after drying have more of beta turns than the random coil or helices structure. So and this phenomena was further validated by cosine similarity index, which is a metric to measure similarity between two spectra. So here, when we compared with the native whey proteins, EST powders at pH 7 showed highest similarity, whereas CST powders at pH 3.5 showed the lowest similarity. So you can say that electrostatic spray drying holds a great potential in retaining in the drying of whey proteins and retaining their native structures. Further, we also looked into the surface composition of the powders. So here this black region is the proteins on the surface, and the gray region is the lactose on the surface. So in all cases, like in all pH or cases, we have more protein on the surface in the electrostatically spray dried powders, like 10 to 20% higher protein on the surface on EST powders. Uh, while in contrast to the bulk composition, like in bulk composition, whey proteins were only 15%, but on surface composition, like 55 to 60% of the surface was covered by whey proteins. So it may be due to the diffusion of proteins under the influence of an external charge that we can see more protein on the surface. And further, these are the scanning electron microscopy images of both the powders. So the upper one, blue ones, are the electrostatically spray dried, and the orange ones are the CST drying powders. So they both look similar in microstructure and their sizes in all cases. So the key messages from my presentation would be the electrostatic spray drying made drying at low temperatures possible by applying an external charge. So now you can dry the liquid products at low as inlet as low as 75 degrees. And DSC and FTR analysis showed protein stability during ESD rather than in CST, as we saw. And the surface composition analysis showed more protein on the surface, which I said, maybe due to the diffusion of proteins towards surface. Sorry. Yeah, from these results we could say that it is a promising technique for drying of heat sensitive components. Thank you. Thank you for your attention. I'm glad to have any questions if you have.
Thank you very much for your nice presentation, Paul. Yeah, so really, new topic. So let's see if there are questions. Don't see them yet appearing, but I would like to ask a question then to kick off. So you said that, say, the technique requires that there's a difference between polarity between the solvent and the solutes then, or the other components, and then, okay, you mentioned whey protein might be, but for example, sugars or so, they have a more or less similar polarity, so you assume them not to migrate and influence, so the component should have a charge, or should be really apolar, like oil droplets?
So we believe that so because we have water, so that's
Mhm.
the most polar component in our feed, like in the liquid products. So we can say that the other components would be less polar than the water. So so the polarity would not make much difference because the water is going to be the most polar component of our feed, which is going to be at the outer surface, and that's how the drying is going to take place at low temperatures.
Yeah. Yeah, so the whey protein also moves because it has a polarity, it has a charge also towards the
Yeah,
outer surface. That's how you explain it. Yeah.
yeah.
And then you also, I also see here a question. So it's actually quite common to spray dry at low temperatures. Have you compared CSD and ESD at the same temperature? ESD might delay crust formation and extend constant ray drying, hence reduce drying time. It also seems to allow manipulation of particle structure and component distribution. And so the main question is, I guess, have you compared them at the same temperature?
Both the drying methods, you mean?
Yeah, because
Yes,
then the
yeah,
constant rate
yes,
regime is the same.
yeah. Yes, so for the same product, we have tried the same temperature for the both dryers, but we were failed to produce any powder from the conventional spray drying method.
Okay. Uh, I noticed a large difference in final moisture content, says something. So I think the ESD moisture content was a little bit higher, probably resulting in other morphology of the lactose. Did you notice difference in amorphous form in the low moisture crystalline or versus crystalline in the high moisture powder for the lactose?
Sorry, again, the last line I didn't understand.
Yeah, maybe did you determine the degree of crystallinity in your powders for the lactose? That could be a difference for the two type of powders if you have them in different final moisture content, I guess.
Okay, well, not now, but we'll definitely keep it in our project, yeah, for future, yeah.
Yeah. What are the difficulties to scale this technology up, or is it very easy?
Well, this technology is already scaled up, but I'm only working on the laboratory scale right
Yeah.
now.
Yeah. It's this company Polar Dry, I think, which is also
Yeah, yeah,
yeah.
yeah.
Okay, and can a dry powder be achieved at low drying gas temperatures with low charges as well? Have you looked into the charge threshold for drying gas temperature reduction? Yes.
Okay. So we did try different charges. Like for this study, we used 10 kilovolts, but we did go up to 20, and we did go lower up to 5 kilovolts as well. So in all cases we could achieve dry powders with satisfactory moisture contents, uh, but there were no like any other significant differences per se in terms of whey proteins structural changes or other changes, yeah.
Okay, so despite the fact that you varied a little bit the electrostatic charge or the electric field that you applied, you did not find any significant
No,
influence on the drying behavior. Okay.
yeah, like for this product, no.
Yeah, did you build a total new equipment or did you use an old spray dryer?
Uh, well, I'm using an equipment that is designed by company Fluid Air.
Yeah.
It's Polar Dry. Yeah, so it's relatively new technology, and they are and it's improving as well.
Yeah. Okay. I have one other question. So you also determine the surface composition of your powders. So which method did you use?
So we used XPS.
Mm-hmm.
Yeah. Like so I did not do it myself, but we outsourced this technology from University of Limerick, Ireland. So they use this XPS technique for surface composition of the powders.
Okay. And is that very quantitative? Because yeah.
Yes, yes, it is very quantitative.
Okay. Thank you very much. Are there any other questions from the audience? Did we answer all the questions? Yeah. So then, thank you once again, Dol.
Thanks,
So,
Marteen.
yeah, and thanks to all the speakers actually, presenting today. Now then we have, let's say, some moment for discussion. I don't know if someone would like to raise a certain point, a common point, let's say a red line across the different presentations. I see also that Boelo has his video on. Maybe all the other presenters can have their video on as well. Would be nice if there are some additional questions that could be stated. So maybe a generic question from my side is, so why does it take such a long time before electrically driven technologies replace existing thermal, for example, spray drying or other convective drying processes? Maybe it's a nice question for Alex. Maybe you have quite some experience. So what is now the challenge actually that you have to convince people to
Let me
replace
express
their
my just personal opinion. What do I think? First of all, it's requires so multidimensional knowledge. Electrical engineering, food engineering, probably hydraulic engineering. It's all of these electro technologies, they are pretty much complicated. And unfortunately, the theory of electrostatic is not really fully developed. So I could feel that we are missing a big conceptually fundamental understanding of all of these electrical phenomena.
Yeah, it's also typically not always in the curriculum of chemical engineering or food technology students programs, so educational programs.
Exactly. And that's what limits actually applications, because multiple factors is very difficult to combine into one picture.
Yeah. Thank you very much for your answer. And of course, we talk about drying, but also about dewatering. Maybe, I don't know if Sarthak is still there. Yeah, I see that you're also still there. Yeah, so also just wondering, so we did not talk a lot about applications of electroosmosis, but I think you also looked a little bit into that. So do you see already some type of applications, let's say, of electroosmosis that are already commercial?
Well, dewatering and drying are fairly new technology or avenues where electroosmosis is now being used or now being thought of being used. But electroosmosis is already being used for soil reclamation, so a lot of civil engineering applications are based around electroosmosis. I've also read paper where they've used not particularly electroosmosis, but streaming potential coupled with electroosmosis to study petroleum reserves in deep Earth stratospheres. You can see that there are a lot of papers on those dimensions. Because electroosmosis is a phenomena mostly used in microfluidics, so you see a lot of applications on lab on chip as well. So the technology itself is very well defined. It is when you need to scale it up to an industrial level, that too where productions are happening 24/7 round the clock for 300 days straight. The kind of reliability you need in terms of technology is something that we are striving to achieve. I think that's the gap that we need to target. The technology is pretty well aware at this point. We're just redirecting it towards a new avenue. That's all I believe.
Yeah. Really trying to push the boundaries. And then if you think about paper production, I saw in the questions 600 meter per minute. It's an enormous speed. And if you want to replace the current technology, you have to really be very smart, because I guess also many people tried, and it's also a matter of increased understanding and design. Thank you, Sarthak.
No worries.
Maybe also for Judith a question. So what will be your next step? So what will you start drying after you optimized your current setup? Which type of materials? Could you say something about it, Judith?
Well, I actually had I looked at Alex's presentation with quite interest, and I totally agree that there's a gap in seeing the different materials that are being dried. And what I think might be very interesting is to see the effect of the material on the electrohydrodynamic mechanism. So I already also talked a bit about how the amount of water in a sample during drying might be affecting the current through the system. And I guess that that's something that I would really want to investigate. But also the type of structure, if it's quite liquid or semi-solid, and the way it's structured after drying, if that has an effect on the ESD mechanism. So I want to vary that a bit.
Okay, thank you, Judith, for a nice answer. And then maybe also for Chutani, maybe also for you the question. So now you dried a combination of whey protein isolate and lactose, but what will be the next material for which you might maybe see an advantage for electrostatic spray drying?
So my project is actually on an infant formula. So we are going to add heat sensitive materials like lactoferrin, or maybe something, or like right now I'm adding lactoferrin in an infant formula with the whey proteins as well. So we are going to look into that next.
Yeah. Maybe also good to realize that in a buggy dryer you collect your sample in a pot that's pretty warm. So I don't know how you deal with that, but also to remove the product fast enough so that it doesn't get harmed or damaged in the pot. It's a kind of a problem in this type of buggy spray dryer. Maybe you already thought about discuss that.
Yeah, thanks, Martin.
Yeah.
I'll surely keep this in mind.
Yeah. Okay, very good. Now then, thanks all the speakers once again, and also Boelo for the nice introduction and Martine for the organization. So then I guess we come to an end of this session. The session is recorded and will become available on YouTube. I don't know if Boelo or Martine wanted to say still something for the audience.
Yeah, thank you very much, Maarten, and thank you very much for all the speakers. This was a great session, and indeed, I think most of it is recorded. A little bit of Alex's presentation is maybe missed after the break, but for most of it, you can all view it back in due time. Maybe not directly tomorrow, but it will become on YouTube available in the next period of time. And for now, I wish you a good evening, and I hope you enjoyed this session.